evening, everyone. My name is Bruce Baer, Dean of the College of Forest Resources. On behalf of the College, I wish to welcome all of you to this three-part lecture series entitled Sustaining Our Northwest World. Our intent in this series is to highlight the dynamic balance we seek in meeting the growing natural resources needs of society while sustaining the environmental, economic, and cultural values we associate with our urban and wildland resources. This set of lectures is a companion to the College's Denman Forestry Issue Series, also seen on UW-TV and the Research Channel. Both series contribute to the College's vision of world-class leadership in sustaining natural resources and environmental services, and both help prompt healthy scholarly debate in our college and throughout the region on ways to improve the lives of future generations while satisfying the needs of people today. In our college, we study and investigate the sustainability and functionality of complex natural resources and environmental systems in both natural and managed environments using an interdisciplinary approach across multiple spatial and temporal scales to include our urban, suburban, and wildland landscapes. We focus on programs in sustainable forestry, sustainable urban ecosystems, and sustainable forest enterprises. Most natural resource decisions are complex, and many are contentious. Good solutions require that objective science be used to weigh the ecological, social, and economic consequences of decisions in order to meet the desired balanced result. All three values must be considered to achieve sustainability and to ensure the proper stewardship of our resources. The concept of sustaining our Northwest world is deeply rooted in the history of our college. Our newly transformed undergraduate curricula honor this tradition while simultaneously capitalizing on the competitive advantages we offer through our location in a major research university. We intend to produce the next generation of natural resource scientists, managers, and leaders who, along with you and other citizens, will ultimately be charged with sustaining a healthy Northwest environment, a dynamic Northwest economy, and the rich social and cultural heritage we all enjoy. Our college has long been recognized as a leader in forestry education and research, and as an integral part of the research enterprise of the university. We intend to build on these strengths by placing renewed emphasis on professional graduate education and research in areas of high impact to society. The ultimate goal is to ensure that our natural resources and environmental systems are sustained into the future. We are pleased to present this lecture series as a partnership between the University of Washington Alumni Association and the College of Forest Resources. We are also grateful for the support of the Rachel A. Woods Endowment, which is underwriting a portion of this series, and to the members of the college's Dean's Club for their unflagging support. Lastly, we are grateful for alumni activities with the college and encourage you to join the Alumni Association if you seek further involvement and want to stay connected.
Tonight's lecture is about the future of bats in the managed forests of the Pacific Northwest. And it is a joint presentation of the College of Forest Resources and the University of Washington Alumni Association, of which the Foresters Alumni Association is a proud part. If you're interested in becoming more effectively involved with the university and with the college, we invite you to join or become more active in the Alumni Association. Our speaker this evening is Dr. Stephen West, and he'll be presenting information which is absolutely fascinating about bat species in the Pacific Northwest. Since the founding of the Society of American Foresters in 1900, the study of forest science in the United States and in North America has become increasingly complex, and the broad field of forestry is indeed a fascinating one. We're very proud of our college for being in the forefront of gathering together the various disciplines that we must bring to bear in doing good forest management. And we're very proud of our college for leading intelligent discussions based and informed by sound science. And tonight's talk is certainly in that vein. So again, welcome to tonight's lecture. Please enjoy.
I think bats are probably up there somewhere with snakes and spiders in eliciting mixed response from the public. They've got a duality there. It's somewhere between fear on the one hand and fascination on the other. They're unfathomable, mysterious creatures. They're well beyond our normal day-to-day living. And so people are a little ambivalent about bats. On the other hand, the more you know about bats, the more you must know about bats. They are absolutely fascinating creatures. They do things that other animals simply don't come close to. So they're truly a remarkable group of animals. So the short answer for tonight, I'll give you the punchline now. Yeah, you're still batty, but you're probably only half as batty as you were 100 years ago. The exact number is difficult to discern, but many indicators would tell us that the bats are not doing quite as well as they have been in the past. But there are things we can do. So, worldwide, bats come in two types. There are Microchiroptera, large hand wings, chiro, hand, and ptera wing. So the Microchiroptera, the old world fruit bats, are really big ones. We don't have in temperate regions, unfortunately. You could go down to Woodland Park Zoo in the Nocturnal House and see them, but they don't occur naturally. They tend to be fruit eaters, and they don't echolocate typically. There are not very many of them worldwide, 160 or so, one family. The Microchiropterans, the small hand wings, the echolocating bats, are much more speciose, the far more species of these worldwide. All of our northwest bats are in this group. They're all Microchiropterans, and beyond that, they're all in one family, the evening bats of the Vespertilionidae. There were several other lineages in bat history, but they're now extinct. So we're down to just the two major groups. It just really disappoints me that we don't have these locally. Flying foxes are just spectacular animals, but they just don't occur in temperate regions. They are a group of conservation concern. They're eaten as delicacies in some cultures, and in others they're persecuted for their competition with fruit growers. It's kind of an irony because these are the animals that pollinate many of the tropical trees. So it's a difficult situation. Worldwide, the Microchiropterans are not doing particularly well. The Microchiropterans are cosmopolitan. They are absolutely everywhere. And if you think about what these animals do, they have no business being in cold environments, right? They're little tiny homeothermic things, but they're tricky. They do things that are truly remarkable, allow them to invade niches you would never expect them to be in. They're everywhere but Antarctica. They're absolutely worldwide. In temperate regions such as ours, they're insectivorous exclusively. But as you move into the tropics, bat feeding habits become quite diverse. And we've got bats that eat fruit, of course, like the Microchiropterans. We've got micros that eat fruit as well. They also feed on fish. There are fishing bats with big claws that skim along the surface of the water and pluck up small minnows and things. There are bats that specialize on eating other bats, bats that are frog specialists. Listen for frog calls and nail them. Bats that feed on nectar and pollen, and of course, blood. Now see, there's a vampire bat. That's not the most fearsome face you've ever seen, is it? But that's one of the vampires in the New World. Of course, that's the only place they occur. So Microchiropterans are fascinating for their diversity. They show every conceivable mammalian reproductive type. They're the only ones to show certain reproductive modes. A common one, I'll just mention this because it bears on their conservation. A common mode here is known as sperm storage, where these bats get together at the hibernaculum with males and females to spend the winter. They breed at that time, but there's no fertilization at that time. Female stores the sperm until she's ready to fertilize the next spring. So if it's a late winter, she just waits. So there's a facultative adjustment. They wait until there are food supplies and that things are warm enough. At that point, fertilization takes place, gestation proceeds, and they have the young. So males don't help in the raising of young at all. And there's often a remarkable separation in space between males and females once they leave the hibernaculum. Some species, like the cinereous bat, the hoary bat, which is up here, our largest bat, we have mostly males on the west coast. Females are back east having young. If the males that don't interfere with the food supply of their females and young leave more offspring. So they just get out of Dodge. It's an interesting strategy. They undergo torpor. They save energy both daily and seasonally by hibernating. So that's one of the keys to them inhabiting very adverse environmental conditions. And all the microbes echolocate. So here's the southern long-nosed bat is a pollen, a nectar feeder. I've mentioned the vampire bat, and that's the last thing a flying nocturnal insect ever sees, right there. So we have 16 species by generous count in Washington. 4 of these are desert species. They're over in the Columbia Plateau, the sagebrush and basalt columns lands. And I've got a couple of them up here. You can have a look at them after the talk. One is the pallid bat. It's the largest desert-dwelling bat. Then there's the western small-footed. I have that one here as well. And the pipistrelles are our smallest bat. We don't have one of these at the Burke Museum. We ought to work on that. But a very tiny bat, only in the desert. And then, one worthy of 2 photos in my slide, the spotted bat, which we didn't have strong evidence was here until 1991. So it's a recent addition to our bat fauna. It only occurs in washes with, as far as we can tell, cliffs and water. And it's the only bat we have that echolocates in the range of human hearing. So if you go out there, take the Vernita Bridge and then go north up into Frenchman's Coulee or one of those watered coulees, they seem to be in the watered ones, and listen, you'll hear, and that's a spotted bat flying around. It's echolocating about 9 to 11 kilohertz, and you can hear it. All the rest are beyond our range. We've got 12 that live in the forests. Big brown bat, a very common animal here, as it is over North America. And he's up here. The western red bat is known from echolocation calls only up in the Okanagan region. There are specimen records in BC, none in Washington. As far as I know, none in Oregon. So we may have it. And if we don't, we've got 15 bats. The hoary bat is our biggest bat. And it's a foliage rooster. It's a little different from a lot of our other bats, which are crevice roosters. These will hang up in a branch, and they don't need specialized structures such as the other ones. We'll talk about those. And the silver-haired bat is up here as well, a very common forest-dwelling bat. Townsend's big-eared bat is a listed species, both state and federal. It's got problems because it's the only bat we have that seems to require caves for overwintering. And we don't have a lot of caves in this part of the country, as you know, and the ones we do have people in them all the time disturbing the bats. These are quite intolerant of disturbance, and they're not doing well. And they are a concern, both at the state and federal level. The largest group of bats, by far the greatest number of bats, are in the genus Myotis. We've got 7 species here. We call them collectively LBJs. They're little brown jobs, and they're hard to tell apart. Some of them have rather unique features, but by and large, they're tough. You got to have them in hand, and you have to know what you're looking for. And even then, it's hard to tell some of them apart. I have 3 of them up here. You can have a look, but they're by far the most abundant bats that we have here. Keen's Myotis, this right down here, is a unique bat in our fauna. It's the only endemic bat we have. It occurs just in the Northwest. In fact, Washington is the only state in the lower 48 where it occurs. and its distribution, as far as we know, goes up coastal BC into southeast Alaska somewhere. And we just don't know. This is known from very few specimens. It's a species of concern because it's only known from old coniferous forest, which, as you know, on the west side and the low elevations could be a problem. Okay, all of our bats echolocate, generally in the range about 23 to 70 kilohertz. A hertz is 1 cycle per second, so K is 1,000 of those. You used to be able to hear up to about 18 to 20,000 kilohertz. You probably can't anymore. You can probably hear up to about 15 if you're still in good shape. But bats get started with their echolocation calls well beyond human hearing. And they're used for navigation as well as feeding. The outgoing call is made by the larynx, just like the noises you make. And then they're quite loud calls, actually. They've got a fair amount of energy. And then, of course, they locate, position things, and tell relative motion by the nature of the echo. Bat calls have two phases. A search phase, it's a sort of a series of regular outgoing calls, sort of as they fly along, they're testing the environment, seeing what's out there. And then a phase known as a feeding buzz, this phase here of the call, where they found something like an interesting moth. And as they get closer, they need more and more information about it. They increase the pulse rate, quicker and quicker and quicker. And it's known as a buzz. I'll play you one in just a little bit. It's an interesting feature of their echolocation because it allows us to index feeding rates. So we could compare habitats as to their foraging efficiency by just counting the buzzes, which are very distinctive. Our bats don't form huge colonies in the Northwest. This is an important feature. As I say, we don't have a lot of caves. Most of the large colonies I'm aware of are in human structures, warehouses and piers, that sort of thing. As long as they're bat-friendly, bats will use them. In fact, all these species pretty much will use human structures as long as they're bat-friendly. They're increasingly less bat-friendly with newer construction techniques. But most of our bats form small groups, small colonies in natural cavities in forest environments, generally large snags. We just don't have millions in colonies the way they do in Carlsbad or the limestone cavern systems back east. They use day roosts, and of two kinds primarily in forests: large live trees. So a lot of people think bats only use snags. That's not true. Large live trees, particularly conifers, as they get older, they get this very rough, rugose, creviced sort of bark. And as they get really old, the bark begins exfoliating, creating like a shingle effect, and bats get all up into there. That's prime roosting habitat for them. A young conifer offers zip. Nothing there for bats. So they need to get quite old before they're used appropriately. And of course, they form the source for large snags, which are primarily where the maternity colonies go, because they have larger cavities within them, so that is the source. We know from radio telemetry work, that's one of the advances I'll talk about, that roosts, they often pick them on southern exposures or edges of forests. They don't do it on the north side of hills. They don't typically do it in riparian zones. And that latter is a big shame, because if you're aware of some of the recent rules and regulations about riparian zones, we're going to be leaving a lot of big trees along riparian watercourse, along the riparian zones in the future. Bats don't seem to like those as roosts. Okay, large snags are very important. They pick these often where there's some sun exposure, and it offers them a thermal choice. They can go warm or cooler depending on what their particular needs are. Cavities are big enough for maternity colonies. And as a management consideration, if we're going to keep these things on the landscape, they're probably going to require some buffering. The labor and industry guidelines do require buffering as snags become infirm, live trees around them to help protect people that would be in the forest. And we also need to work on replacement schedules, snag replacement schedules. We're thinking about hundreds of years here. Many times we find that roosts are super canopy trees and snags. They really pick out the trees that extend beyond the average canopy height. And we know one reason for this, of course, those are big trees and snags, but there also may be a navigational component here. If you're a bat flying along over the canopy, these are the things sticking up like signposts. They may actually be easy to find and visited much more than you might expect otherwise. So they're important. Super canopy trees are almost always used. Forest succession is an interesting feature in the natural history of bats. Bats use open areas, very early successional areas, grasslands, shrublands, and especially water. We'll say more about water in a minute, for foraging. They use older forests with potential roost sites in them for roosting. And as I'll show you with data in a little bit, this stuff is essentially a bat desert. Okay? They split up the landscape between roosting and foraging and drinking. They drink each night. High quality habitat has water, food, and a roost in fairly close proximity. Bats hate to commute. I mean, it's the same drill we have. I mean, the shorter distance they have to go, the better, the less energy they expend. Okay, so there's the natural history segment. I want to move on now to a bit on how we know what we know about bats. And the very first work done on bats was kind of crude. It involved work with shotguns and dust shot. So you'd fill the shot shell with dust. Basically, you'd pick up a pebble, throw the pebble in the air, shoot the pebble, and the bat would be diving for the pebble, and you'd get the bat. If you look at old collections in natural history museums, the bats have this strange moth-eaten look. They've got holes in their wings, and they don't look too good. That's not moth work, that's dust shot. So there are obvious limitations to the use of shotguns in studying bats. Later in the 20th century, mist nets came into being. Mist nets were used, of course, for a lot of bird work, small birds, and also used for bat work, and had the distinct advantage of allowing you to handle a live bat and let it go, which was a big plus. Mist nets were pretty much the rule until the late 1960s into the early 70s, and people began using different ways of catching bats. I'll talk about harp or Tuttle traps in a minute, which are an advance in many respects over mist nets. Radio telemetry, I've mentioned a minute before. Radio telemetry has been around a long time, but it wasn't of much use for bats. The radios that were available early on would basically crush one of my LBJs. The idea of keeping the weight of the package below 5% on a flying animal really didn't make it an option. But now miniaturization has become so good, companies like Hollow Hill Limited in Canada produce a radio transmitter package that weighs 0.38 grams. 0.38 grams, that's next to nothing. That's with the battery and the antenna. And you can see one attached to a very small bat right here. You basically take a little bit of surgical adhesive and you go and let them go. The transmitter will transmit about a mile and last about 3 weeks. So you get all kinds of information on roost characteristics during that time. And then hopefully the neighboring bat grooms the other bat, pulls the transmitter off while the transmitter's still ticking so you can go get it and replace the battery rather than throwing your $160 investment away, which happens all too often. Echolocation detectors, that's the newest toy. Obviously, it's resulted in an explosion of work on bats, and we'll talk about that right now. Harp and Tuttle traps, they're an ingenious design. The first time you see a harp trap, you go, that can't possibly work. It's just not believable. It's a simple frame. In this case, the ones we use are about 2 by 2 meters. It's an aluminum frame and a bank of vertically strung fishing line, just monofilament. There's one bank, it's about a 1-inch spacing between the vertical strands, and then a second bank behind that one, about a couple of inches, it's offset. And so the second bank is right in the middle of the spacing of the first. And there's a collecting canvas bag in the bottom and a little flap of plastic sewn into the top of that collecting bag. A bat flies along, sees this vertical bunch of clutter, and being the maneuverable animals they are, it's no problem for them to fly through a 1-inch vertical space. No problem. They just turn on edge, go right through that first space, and then, there's another strand right there. And so they go flop, 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 and they slide down in between the monofilament banks and into the bag. They crawl up out of the bag and end up under the flap of plastic here, and you can see a couple of LBJs roosting there. They get up there, they realize they're not going anywhere, they shut down, go into torpor. You go out the next morning and there they are. Very easy to handle, they're sound asleep. You can take the measurements without being chewed and cursed at, and then put them in a pocket, let them warm up, and they fly away when they're ready. It's easy on the bats, there's not a lot of trauma associated with this, and it's easy on the batters. You can run several of these simultaneously. You can't do that with a mist net. You've got to be at the mist net location at all times because the bats get all tangled up in the mist net. You have to get them out. These are fairly straightforward. So they're great advance. They work well in restricted flyways. They don't sweep a lot of area. Like a mist net, we could string all the way to the back wall if we wanted. So mist nets still have their place. But over small water courses, exits of buildings, exits of mines and caves, they're fabulous. You can catch 20 or 30 of these in a night. You have to be devious. You must be thinking one step ahead of bats. These are animals that live a long time, 30 years, for example. The smallest ones, there are records of California Myotis living in excess of 30 years, banded as adults. Okay, so they're smart and they're not easy to catch at all times. They forage over water extensively, so you can take 4 traps, like we have done here, hang them from a bridge, close off the flight ways to the left and right and across the traps, and just clean up, catch a whole bunch of bats. Or you can do this on trails and roads. You go out and put a big tarp up and leave it there for a week or 2. The bats get used to flying through that little space, which just coincidentally happens to be exactly the dimensions of a harp trap. And then you sneak out one day and stick the trap there, and they all get caught. It's really fun. You end up with about 30 or 40 bats. It's really good. Okay, echolocation detectors. This is the newest technology. All of our bats are echolocators, and we can't hear them. But these devices take the ultrasonic call, divide it by a divisor, a division ratio of your choice, and then allow you to hear it, essentially. So the system we use consists of, this is made by David Titley in New South Wales, Australia. It is the detector, that's this box here. So the detection system consists of the detector, a delay switch which turns the whole system on and off, has a photoelectric cell on it, and improves the efficiency of the call, a rechargeable battery that runs the whole thing, and a simple voice-activated tape recorder. That's all you need. Do the whole thing for about $750. Completely automated system, turns itself off and on, records the call, tells you the time, and puts a calibration tone on the tape. So the next day you go out, you got a tape full of bat calls. Pretty slick. The detector in close-up, you can come play with these, I say afterwards, consists of a broadband microphone which takes in the ultrasound and basically converts it via the division ratio to an audible sound range. It depends on how high the frequency of the bat is as to what division ratio you use. We use 16. This goes from 4, 8, 16 to 32. 16 works for all Northwest bats. If you were in the tropics, you might have to use 32 because some echolocate as high as 300 kilohertz. Way up there. So you've got a sensitivity switch, which increases or decreases the sensitivity of the circuit, an on-off switch, volume switch, and a calibration tone, which is set at 40 kilohertz, so you know where the bat call is relative to the calibration. And they sound like this. That's the call of Townsend's big-eared bat. That's what you would hear coming out of the speaker of the detector. So that's how you get the call, and then once you've got it, you've got a tape recorder full of arcane messages, and then you want to do something with those, you get the Anabat digitizer, which is a simple digitizing circuit. Connect that between your PC and the audio tape, play the tape, and it basically converts your analog signal to digital. You can save it as a PC file and display it with the Anabat software and you get a frequency time display. I'll show you what it looks like in a second. Anything electronic you take out in our northwest woods, you know is a problem, right? So you've got to button these up a bit. We use a high-tech system of a nice Tupperware box with a hole cut in it for the microphone and a little awning of plastic that we snap over the top. When you're working, if you're doing field work, simpler is best. So this works pretty well. We put it about 3 feet or so above the ground and orient it. We tilt the whole box up about 30 degrees. That makes the cone of detection. It clears the ground and gives us a maximum flight space for detection. And this is what you get. So this is the software from the Anabat system. You get a display like this. There's 2 calls here. It's a frequency on the y-axis and a time x-axis. And basically, you've got a header which explains some features of the call, and then you've got the call itself here. And the big brown bat, that's the top call. Did you get the buzz? So this is the search phase, the individual click, 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 and then you got that strange sound, the buzz. That's a dead bug. Every time that happens, a bug has died. The lower one is somewhat higher frequency. That's the Yuma Myotis. It's one of the higher frequency bats. So you can see there's some differences. You could tell a Myotis from a non-Myotis. The lowest frequency in the call and the shape of the call are really good diagnostic features. We can generally tell most of the different genera apart. They're distinctive enough in their calls to where we usually can tell them apart. When you get to Myotis, all bets are off. The LBJs are about the same body size. They tend to do about the same thing, so it's not surprising their echolocation call structure is very similar. They overlap enormously. We have to lump them. So we tend to analyze things Myotis and non-Myotis, or to genera that other than Myotis. So bat activity in the Northwest, foraging activity and raising of young are successful enterprises if there's an adequate food supply. And so bat activity is keyed to the abundance of nocturnal flying insects. And you know you don't get a lot of bugs flying around when it's pouring down rain, or it's cold and pouring rain. That's the worst possible situation. Bugs like warm, dry nights. And so bat activity and numbers are tied to that. So if you look at Oregon here and Washington, where are the bats? They're east of the crest. They're over in eastern Oregon, eastern Washington. By far, more of them are there, and virtually all the populations over there are breeding. You come west, the activity levels drop rather dramatically, and you find high activity of bats only in rain shadows and at low elevation. As you move from the low elevations on the west side up into the Cascades, what happens is you move away from the breeding females, you get into non-reproductive females and males. So the low elevations on the west side are very important for bat breeding success. It obviously has importance for their conservation. So you're a bat, you're living in western Washington, where are you going to spend your time? Yeah, San Juan Islands, Squim. You're not going to be anywhere else. And it's interesting, in this chart here, the highest number of bat calls per night, the average is at Little White Salmon, which is just east of the Cascade Crest. It turns out that detections we have from San Juan Island are just the same. So they're essentially, that rain shadow is almost the equivalent of eastern Washington in terms of bat activity. So if you got to be in western Washington, you got to study bats, go to the San Juan Islands. Okay, now you're suitably armed. Let's talk about the results of the studies we've done. I'm going to talk about 3 studies. I'm going to give you a quick thumbnail for each one. 2 of them are timber fish and wildlife studies sponsored by the state of Washington. The first one is a study we did. It's really just a survey. All of these are Anabat echolocation surveys, so we're looking at activity. And this is done in managed forests northwest of Mount Rainier National Park. We chose 4 stand types that are very common in managed forests. I'll show you pictures of them in a moment. We had 6 replicates of each one. We visited each site 8 times each year for 3 years running. So this is a pretty intensive sampling. It's a survey, but it was an intensively done one. And there's some interesting things that came out of that. The second one's also a TFW study. It was a companion one looking at riparian zones, which are important for bats. It was a large experiment. We looked at 2 years before we harvested the sites, 2 years after the sites were harvested, and we looked at narrow and wide buffer strips along the riparian zones that we were interested in. So we had 3 conditions. We had narrow buffers post-harvest, wide ones post-harvest, and unharvested riparian zones. 6 replicates of each for a total of 18. We'll show you the results there. There were some big surprises in that study. The last one we've just concluded. It's a Forest Service study, demo project, demonstration of ecosystem management options. It's another large experiment, 2 years before and 2 years after harvest, where we varied the amount of green trees retained after harvest and their pattern. And it's kind of a complicated design, so I'll show you a slide of that in a moment. We had 6 treatments in each of 6 blocks. 4 of the blocks were in Washington, 2 of them were in Oregon, for a total of 36 sites. A fairly major study. So the TFW landscape study, the survey of what's out there on a managed landscape, we looked at 6 recently harvested sites. The detector would be out here on a stump somewhere away from the edge. We looked at sites that were pre-commercially thinned. It's right just before canopy closure, kind of a transition between open fields and closed canopy forest. We looked at dog hair, unthinned, young, very dense stands. These cover an all too large acreage in the Pacific Northwest, as you probably are aware. Very high tree density, no understory essentially, not much production at ground level. And the last stand type we looked at were harvest age sites. In this system, about 55 years was the average harvest age. Now, these are stands that have been entered twice, so they've been pre-commercially and commercially thinned, so they're much more open than they would be otherwise. And they've also got understories, and they've got, as you can tell, pretty good level of ground development. So those were the 4 conditions we looked at. This is what the bats thought. Here's the grand mean, and here are the types. The first one here is the harvest type. This is the transition between open country and closed canopy forest. That's dog hair. And here's the harvest site. Take home here is the highest activity and the highest foraging rates are in the harvests, the open areas. The bats were using those rather extensively. Intermediate levels in the harvestable age stands. Not much foraging activity there. They're using those as roost sites. A lot of activity early and late, so they're coming and going out of those stands. Pretty low activity in the transitional stage, and here you go. 6 sites visited 8 times, 3 years running, not one bat call. An absolute 0. That's bat desert, folks. They don't use it. The second study, the TFW riparian study, we were very interested in working on this one because bats in particular use water bodies, as you know, as primary foraging sites. So if you were to look at the activity over a pond, say, versus an upland forest, even an upland clear-cut, for example, where we know they're foraging quite a bit, it's way higher. It's like 1 order of magnitude higher. They use them intensively, and bats drink every night. So they need to be near a water source. So we're quite keen on doing this study. We know from radio telemetry work they're not used as roosting. I've mentioned this already. It's too bad because it could have solved a lot of problems. We suspect it's related to the cold air drainages along the creek bottoms. So what did we find out? The TFW study was very interesting. What you're looking at here are our 2 harvest blocks. Recall that we were in there 2 years before any of this was removed, so we were in there in an intact forest studying the riparian zone used by bats and both of these sites. Then we came in, harvested them, creating a narrow buffer, that 45-foot job, and then a wider 100-foot one. State guidelines for state and private lands don't allow a buffer zone that narrow any longer. We're in this ballpark now, about 100 or so. It turns out, interestingly, before harvest, the only thing really in those riparian zones were Myotis bats. The very small, highly maneuverable bats who were working their way through those riparian zones. It was basically Myotis habitat. After harvest, some interesting things happened, and some things we did not expect. And that was that the bats were using these scrawny little buffer zones at the same rate they were before the forest surrounding it was harvested. There was no difference statistically before and after harvest. They're just going along, minding their own business year after year in that tiny little zone. So we saw no difference between these and no difference between control and treatment. The non-Myotis bats, however, their activity went way up on all harvested sites. So there was quite an increase. They're less maneuverable. The non-Myotis bats are bigger bodied, less maneuverable, faster flying, and they use more open areas for foraging. That was a surprise. We just figured there would be no bats in there. I mean, it's just not right, but that's the way it was. If you think you know something, do an experiment. Okay, the last study, the Forest Service demo study, is an interesting one. And if you're flying from here down south someplace, you may see this one. You may have seen it already and wondered, what the? We'll see that in a second. We varied the amount of green trees retained and the pattern of retention. So we went from controls where nothing was harvested, 100% retained, 75% retained. We punched 3 2.5-acre holes in there. 40% retained was retained in 5 2.5-acre clusters or remnants, and 15% retained in 2 remnants. And at the 40 and 15% retention level, we looked at clusters like this as well as dispersed, or basically a big thinning, to see if that would make a difference. Okay. Well, there you go. That's what it looks like from an airplane. It's one of the most bizarre looking things from the air you could ever imagine. So here's the 75% aggregate where we've got the holes punched in, and here's the flip side of that where we've retained trees in the aggregates at the 40% level. So for those of you who know the game, that returns 6 to 5. These are more standard green tree retention strategies. You've seen thinnings like this. There's nothing unusual here except the number of trees is less than the 15% dispersed harvest. What did the bats think of this? Myotis bats didn't care. That's like 90% of our detections. You know, and you're out there and you've got 8,000 something detections and you've struggled through God knows how many hours of recorded tapes and you've done all the analysis, and the answer is they don't care. I mean, it's kind of deflating. But it's good news from a conservation standpoint. There was slightly higher activity, but biologically speaking, it was a wash. They didn't respond. They didn't go down. That was the good news. Non-Myotis bats had higher activity as more trees were removed. So the fewer trees you retained, the non-Myotis, the big bats, responded with more activity. And the activity levels were higher when you clumped the retained trees rather than had them dispersed. So if you had a choice, if you were a non-Myotis bat, go ahead and harvest that thing right down to 15% and leave the remaining trees in 2 clumps. Thank you very much. Maybe that wasn't what we expected. So those are the real quick summaries, the take-homes on those 3 studies. And kind of thinking about putting them together, what does it mean for bats in a managed forest environment? It means that the activity is remarkably variable from place to place, but that variability is predictable. It's always highest in early successional openings, recent harvest, whatever removes the forest canopy, they're using those as foraging areas. The foraging rates are high there. They're using standing trees with suitable roosts as roosts. Foraging rates are low there. And they're not using this stuff at all. So it's interesting and predictable. So as we've moved from really a region of old forest to a region of mosaic young forests of different structure, you know, we've done some things that are predictably not so great for bats. And the most important things, we've lost roosts over time. Large living trees and snags, particularly in intensively managed landscapes, are not prevalent any longer. We've created dense, uniform stands with a very simple vertical structure. Bats fly around in old growth like this. There's a lot of gaps. There's a lot of foraging space even within the forest. This doesn't have that, and so there are problems for bats. Something that's not been investigated that should be is the role of changes in the food supply on bats. I'm sure there are interesting differences in the diversity, perhaps abundance, maybe not abundance, but certainly diversity of insects available as prey in old forest versus this sort of thing. But it's not really been looked at. I mean, it would be an interesting line of investigation. So, region-wide, these are the big no-nos for bats. The number one problem for bats in this region has little to do with forest management. It has to do with forest preservation, keeping the land or the acreage in forest. Jerry Franklin at the last talk talked about this at length, and it's the number one concern. It's not just the concern for bats, it's a concern for all vertebrates. You simply can't have a healthy bat population, a healthy population of amphibians, small mammals, breeding birds, anything, in a parking lot. Okay? It doesn't work. So that's the major challenge, the number one challenge. Keep it in forest cover. That is not going to be an easy task. If you are successful in keeping it in forest cover, the bats, I think, can be dealt with very well with relatively minor adjustments to the way we're doing business. We know we've lost large trees and snags, and that's causing bat declines. We've created large acreages of very dense young forests that are not used as habitat at all, further giving us declines in bat numbers. As an observation, it's probably the case we've lost. It's impossible to know because there's no way of dealing with numbers in history with bats. My guess is at least half. It could be lower than that in terms of the bats we have now. But there's probably been a proportional shift, too. Knowing the responses we've seen in our studies, it looks like the non-Myotis bats aren't doing as badly. I mean, their habitat seems to be okay. They probably have increased proportionately at the expense of the Myotis bats, which were undoubtedly the most dominant group here when the region was covered in old-growth forest. Let's take a look a little more closely at differences in west versus east. You know, there's some big differences in terms of the quality of habitats for bats. Not so good on the west side and much better on the east. In fact, on the west side of Oregon and Washington, you don't get much further north from here, you start losing species one after the other. By the time you get up to Alaska, you've got one left. Far continental parts of Alaska. There's a little brown bat, makes it all the way to the Brooks Range, and it's the only one. So we're right on the margin of what most bats can tolerate here on the west side. Reduction of wetland area has undoubtedly had a major effect on bats. They use those extensively for foraging, and we have drained wetlands with a vengeance on the west side. Not just for human development, but growing trees do better when they're not sitting in soggy soil. So the beaver dams that were on every little stream historically are gone, basically. It's a much drier place, and foraging opportunities for bats have been reduced. Interestingly, though, on the east side, things are probably just the opposite. With irrigation and the implementation of cattle ponds and areas for livestock to drink, I'm guessing bats have benefited from that on the east side. There are probably much more areas that are closer to water that are used now than there were historically. Here's the problem on the west side, these last 2 points, having to do with breeding habitat. Recall, that's lowland forest. That's where the females and the young are. That's where we have built our houses. That's where all the urbanization is taking place. It's also where the forests are most productive and where private companies are growing timber most intensively and have changed the character of the forest the most. So they're kind of getting the bats are getting a double whammy on the west side. Not only is the acreage in forest reduced, but the nature of that forest has changed dramatically. My concern is for bats on the west side. I'm less concerned with bats to the east. Recall that to the east, much warmer, better food supplies. The bats breed there way high in elevation. They're really almost all breeding populations on the east side. Jerry last time talked about a change of view within the Forest Service. National forest lands may be managed for somewhat older forest characteristics in the future. My guess is if that happens on the east side, there's really not much that needs to be done there. The bats there will be just fine under that kind of a different regime. I think on the west side, it's not going to matter. There's not going to be any help for the bats, even if that policy maintaining older forest structures goes into place, because those are too high. They're out of the breeding range. Attention on the west side is going to be on production lands, intensively managed lands for timber production, lowland habitat. So what do? There's really three things. The first one you can do for natural systems of all kinds, and that is let's keep some forest cover. Let's not have row houses to Snoqualmie Pass. I don't think that's something everybody wants, but it's going to be a major challenge, going to require some creative thinking to bring this about. If you're successful in not converting forests permanently to some other human use, then there's two easy things you can do to solve your bat problem. The first is, and I don't know which order I'd put these in, they're probably equally important, thin the young, dense stuff. It's zero stuff. It's not used at all by bats. It's just not a good thing. Now, that's an economic challenge, of course, because you lose money thinning these things. How many fence posts do you need in western Washington? On the other hand, I know of a study that the college potentially will be involved with fairly soon, taking some of that thin stuff out, making methanol out of it, drive around in our vehicles with the methanol, and have the revenue from that pay for the thinning. So it's going to require different ways, creative ways of dealing with this problem. But I don't want to wait 150 years for nature to take its course there. It's likely that before 150 years rolls around, it's going to burn or the bugs are going to get it. So I just assume we got on with it and created better habitat for bats in the short term. It's not just for bats. On the surveys we did showing essentially no use by bats, we also were surveying amphibians, terrestrial small mammals, breeding birds, a disaster for every group. It's crummy wildlife habitat. We need to get rid of it, convert it to an older forest structure. So how many live trees do we need? It's kind of an envelope calculation I did the other day. Small bats will fly a quarter to a half a mile. Half a mile is kind of their upper limit, so that might be an energetic upper limit. If you picked a quarter mile as a radius of movement around a roost, you got about 125 acres or so. We know these things use 6 to 8 roosts in a given place. They don't stay in one roost all the time, they move around. They use a half dozen of them or so. And if you wanted to give them some choice, say, pick 10 out of 20 or 8 out of 18 or something like that, you'd need about one big tree or snag every 7 acres. That doesn't sound like a huge amount to me. 7 acres is a pretty good size area. If we could manage one tree per 7 acres, we would take care of the concerns of forest-dwelling bats, all 10 of them. The other ones are roosting bats. We don't need to worry about large-scale trees for those. We take care of the bat problem just like that, and it also takes care of the pileated woodpecker problem and a whole host of cavity nesting bird problems at the same time. That would also provide 100% habitat for pileated woodpeckers. So 1 tree per 7 acres. Could we afford that? I don't. Something to think about. It looks like these things are possible. We could get by with doing just those two things. Thin the forests, provide large roost structures, and get away with it, because the studies that we've done seem to indicate that bats are willing to trade that interior gap foraging space in an old-growth forest for a situation with open areas near roost areas. So they will fly back and forth. They'll do the commute rather than do their business all within one forest block. To the extent that's a flexibility they have, we could certainly get by with a production landscape and a full array of bats, simply maintaining a few roosts on the landscape.